All right, so let me go to the evolution of mathematics. I'm not going to talk about this, but what I'm going to answer, the question I'm going to answer is why we care about the development of other science. Okay, so in order to answer that question, I need to answer this question. And the way to develop mathematics, there are two ways, to my mind. The first way is generalization. So that's what we mean in the beginning, in the Wikipedia. Mathematicians seek out patterns. What do we mean by seek out patterns? When we see something is correct, we want that particular theorem or particular result is true in a more general case. So this is called a generalization. So this is a good time for me to introduce, to explain my own field. What is differential geometry? So differential geometry, by definition, is the calculus. Everybody knows calculus. A calculus not on a flat space, but on a curved space. Okay? So differential geometry becomes very important because of the general relativity, Einstein's general relativity. Because Einstein believed that the universe we live in is not a Euclidean space. It is a curved space. Okay? It's a space that is much more complicated than the Euclidean space. So it is more natural to, so in order to understand general relativity, differential geometry becomes the necessary piece of it. And because of the definition, differential geometry is equal to calculus, it's very easy to justify the word differential, because calculus, after all, is differentiation and integration. Okay? So how to justify the word geometry? So when you do calculus on a curved space, what do we mean by geometry? Well, as I said before, in order to study geometry, we have to go through the indirect way. And by working on calculus, we can get the geometric information. Okay? This is similar to that to astronomy, for example. So if I just stand here or just walk around, I will never realize our Earth is a round ball. What I will realize is our Earth is a flat space, it's flat. And only if when we look into the sky and we study stars, then we realize, by doing a lot of work in astronomy, a lot of work in mathematics, then we will realize that our Earth is not flat, it is a ball. Okay? So the same thing happens in differential geometry. We want to study geometry. We want to know the geometric property of the curved space. But we cannot do it directly. We have to study the functions. We have to do calculus on that. And the more calculus you do, the better understanding of the curved space underlying. So this justifies the word, the differential geometry, and this is a very important field in mathematics. And it becomes even more important because Einstein's general relativity, it becomes more important because the universe we lived in is a curved space. So the real thing we need to do is differential geometry, not just calculus on flat space. Calculus on flat space is just approximation of the differential geometry. It's just part of the differential geometry. So that justifies the importance of that very interesting and important math field. Okay, but I'm not going to say more about the generalization. So the second thing is, so this is, we want to take care of the development, keep an eye on the development of other science. It's like just a bionautical creativity engineering. So the so-called bionautical creativity engineering is we just get some new ideas and hints by looking at animals. Okay? So animal can use their energy in a more effective way. Animal can fly, animal can walk faster. So we get some hint and do some manufacturing, do some engineering. So this is called bionautical creative engineering. So for mathematics, we also need to get hint, get ideas from other sciences. For differential geometry, the most important source of ideas and the tricks are from the so-called string theory. So from now on, so for the next 5 minutes, I will be very technical in explaining my works. So As I said, physics has a model called mirror symmetry, and there's some mathematical implication from mirror symmetry, one of which is so-called BCOV conjecture. So BCOV refers to 4 physicists, Boltzmanski, Saccotti, Oguni, and Vafa. They made the following conjecture in 1993, which says, okay, so we have, I said Calabi-Yau manifold. Just imagine this as one universe, one Calabi-Yau manifold corresponding to one universe. Okay, so we have 2 universes. They are mirror to each other. Okay, through some strange mirrors, they are related, so that the so-called quantum field theory over it are the same. Okay, and they conjecture that on one Calabi-Yau manifold, on one universe, you can compute a invariant, which is a function, using symplectic geometry, some kinds of geometry. You can compute it, get a function called f capital A. And on the mirror Calabi-Yau manifold, on the mirror universe, you can do some complex geometry and you can cook up with another function. That's called FB. Okay? I will explain what FB in a minute because myself and my collaborator proved the second part of the conjecture. So what they conjecture is FA is equal to FB, which is quite surprising because there's a complete 2 different worlds, and FA and FB are coming from different sources. FA is coming from something called symplectic geometry, which is another part of some branch of geometry, and the FB comes from my field, complex geometry, and for some mysterious reason, for some physics reasons, they have to be the same. So this is the contents of the conjecture. And this conjecture can be split into 2 because we can say conjecture A, compute FA, conjecture B, compute FB, and then you compare FA and FB. Okay? So let me just say a few words about the setting up of conjecture B. So I said by working on complex geometry, I can come up with a function f capital B, how it is defined. So let X be a compact Kähler manifold. So it's quite technical. It's a curved space. Okay, it's not a Euclidean space. It's some, you can think it's a ball. It's a sphere. Okay, and let delta be the so-called Laplacian operator on that compact Kähler space. So the Laplace operator is a very important operator in science and in engineering, but well, it's still technical. And we want to pick up the spectrum of the Laplace. So I'm not going to define what the spectrum is, but a good explanation, a good interpretation of the spectrum is as follows. If we think about these compact Kähler manifolds as a drum, okay? If we hit the drum and we can hear the sound from that drum, and then this sound is the linear combination of all the sounds of different frequencies. And by definition, the spectrum is the set of all frequencies if you hit a drum. Okay? So suppose the Kähler manifold is a drum, then you hit it, you get all the spectrum, you get all the frequencies of sounds. And these frequencies are numbers, are real numbers, from 0 all the way. It's an infinite sequence that goes to infinity. So what we are going to cook up is we want to define something called the determinant of Laplace, which is formally or naively defined. It is the product of all eigenfunctions, all frequencies. Okay? And you see, this naive definition is obviously not good because, as we said, those lambda becomes bigger and bigger. So if you multiply those infinite many numbers, which goes to infinity, obviously you will get an infinite number. Okay? So in mathematics, we define such a kinds of things in a quite different way through the so-called theta function regularization. Using complex analysis, we are able to redefine this product in a very reasonable way so that determined Laplace gives us a number. Okay? So this is technical. We use Riemann theta function to do that.